We have seen the blue marble before. The photograph taken by the Apollo 17 crew in December 1972 became one of the most reproduced images in human history within months of its release. It appeared on magazine covers and protest signs and the walls of classrooms on every continent. It changed the environmental movement. It changed the way human beings understood their relationship to the planet they lived on. It did all of that because of what it showed, a complete, fully illuminated Earth suspended in absolute black, blue and white and brown, detailed enough to see continents and cloud systems and the curvature of the atmosphere, close enough that the planet still looked large and present and real. That photograph was taken from a distance of approximately 45,000 kilometers, far enough to see the whole Earth, close enough that the whole Earth still looked like a world. The Artemis II crew took their photographs of Earth from a distance of 450,000 kilometers, 10 times farther, and what they saw through the windows of the Orion capsule was not the blue marble. It was something that does not have a name yet in any language, because no human being had ever seen it from that distance before, and the psychological research on what it does to the human mind is only now beginning to catch up to what the astronauts who experienced it have been trying to describe for 50 years. NASA released the official images from the Artemis II Earth observation sessions with the language that NASA uses for official image releases: historic, stunning, inspiring, a new perspective on our home planet. The press release was accurate in every technical sense, and it communicated almost nothing about what the images actually represent as a psychological document, because these images were not taken by a camera mounted on a probe or a satellite or an instrument package designed to produce scientifically calibrated data about Earth's atmospheric systems. They were taken by 4 human beings who had been living inside a pressurized capsule for the better part of a week, whose bodies had been accumulating radiation exposure and cardiovascular deconditioning and sleep disruption and the sustained low-level stress of operating in an environment that requires constant vigilance to survive, and who looked out of their windows at the object they could see in the direction of home and saw something that the word Earth does not adequately describe at that distance. They saw a pixel, a blue pixel, bright against the black, recognizable in the way that a candle is recognizable across a very large dark room, present and real and unreachable in any time frame that emergency response operates within. The official images show Earth. What the crew experienced looking at those images in real time, in their bodies, in their nervous systems, is documented in 50 years of astronaut psychology research, and it is considerably more disturbing than any fabricated anomaly in the cloud formations. The overview effect is a term coined by the writer Frank White in 1987 to describe the cognitive shift reported consistently by astronauts who see the Earth from space for the first time. White interviewed astronauts extensively and found a pattern in their descriptions that transcended individual personality and mission type. The experience of seeing the Earth as a complete object suspended in space, without borders, without the divisions that structure human political and social life, produced a shift in perspective that the astronauts described as instant, involuntary, and permanent. They described feeling a sudden and overwhelming sense of the planet's fragility, a visceral understanding of the thinness of the atmosphere as a protective layer, a cognitive reorganization of their relationship to other human beings, to political conflicts, to the things they had considered important before the moment of seeing the whole Earth at once. The overview effect, as White documented it, was primarily described as positive, expansive, a broadening of perspective that most astronauts reported as one of the most significant experiences of their lives. But White's research was conducted primarily with astronauts who experienced Earth from low Earth orbit, from the International Space Station at 400 kilometers altitude, from the shuttle missions that rarely exceeded 600 kilometers. At those distances, the Earth is not a pixel. It is a landscape. It fills a significant portion of the visual field. The details of continents and ocean color and weather systems are visible to the naked eye. The cognitive connection between the object in the window and the home that it represents remains intact because the object still looks like a home. At 450,000 kilometers, the cognitive connection breaks. This is not a metaphor. It is a neurological description of what happens when the visual system receives information that the brain's prior models cannot adequately process. The human visual cortex evolved over millions of years to process information about an environment where Earth was not an object that could be seen, but the surface you were standing on. The idea of Earth as a distinct object with a boundary and a position in space is an abstraction that the intellectual mind can process, but that the emotional and instinctual systems of the brain have no evolutionary preparation for. When an astronaut in low Earth orbit looks at the Earth, they are seeing something their intellect tells them is the whole planet, but their visual system processes as a very large curved landscape, something that the brain can map onto familiar categories of experience, even imperfectly. When an astronaut at lunar distance looks at the Earth, they are seeing something that is visually indistinguishable from a bright star, a point of light. Their intellectual knowledge that this point of light contains every person they have ever known and every place they have ever been is processed by the cognitive systems. Their visual and emotional systems receive a point of light. The gap between those two simultaneous experiences, knowing intellectually what you were looking at while your sensory systems report something that looks like a star, is where the psychological research gets complicated. The astronaut Ron Garan, who spent 178 days on the International Space Station, described the overview effect in a book as a tragic beauty, simultaneously the most beautiful thing he had ever seen and a source of profound sadness at the realization of how fragile the planet appeared and how indifferently the universe surrounded it. Garan was in low Earth orbit, where Earth still filled most of his window. Edgar Mitchell, who walked on the moon during Apollo 14 and therefore saw Earth from the distance that the Artemis II crew experienced, described something more extreme. He described a sudden and overwhelming sense of the universe as a conscious and intelligent system, and of his own understanding of reality as fundamentally inadequate to the experience he was having. Mitchell spent the rest of his life trying to find frameworks adequate to describe what looking at Earth from lunar distance had done to his understanding of his own existence. He was not describing inspiration. He was describing a cognitive event for which no prior category of human experience provided adequate preparation. The psychological research literature on what Edgar Mitchell described and what other lunar astronauts have reported in various forms refers to it now as the overview effect's more intense manifestation, a version of the cognitive shift that occurs not when the Earth is large enough to look like a planet, but when it is small enough to look like something you could lose. The specific psychological mechanism that researchers believe produces the more intense response at lunar distance involves what cognitive scientists call the scale shift effect. Human beings have a cognitive system specifically dedicated to processing social and emotional significance of objects and people in their environment. This system, sometimes called the salience network in neuroscience literature, assigns emotional weight to objects based on their size, proximity, familiarity, and relationship to the self. At low Earth orbit, the Earth is large, close, familiar, and obviously related to the self. The salience network processes it as enormously significant, and the emotional response is correspondingly intense in a positive direction. At lunar distance, the Earth is small, distant, and visually similar to thousands of other objects visible in the same field of view. The salience network has no protocol for correctly weighting an object that the intellectual mind knows to be the most significant thing in existence, but that the visual system reports as a dim point of light smaller than the astronaut's thumbnail. The resulting cognitive dissonance between the intellectual knowledge of what the point of light is and the visual system's report of what it looks like produces a stress response that researchers have documented in the debriefs of astronauts returning from deep space missions, and that the psychological preparation protocols for extended deep space missions specifically address. The Artemis
NASA called these photos a triumph. They released them with press statements about inspiration and a new generation of explorers and humanity's return to the moon. And when I first saw them, I understood why. The resolution is extraordinary. 8,000 pixels of lunar surface rendered with a clarity that makes the moon look close enough to touch. The Shackleton crater at the lunar south pole, rendered in a contrast so sharp that the boundary between the sunlit rim and the permanently shadowed interior looks less like a geological feature and more like a wound that never healed. These photos are genuinely extraordinary, but the longer you look at them, the longer you sit with what they actually show rather than what the press release says they show, the more the triumph narrative starts to develop cracks, because these photos are not just images of a beautiful, desolate landscape. They are a technical document, a record of an environment that the 4 human beings aboard the Artemis II spacecraft flew through at 49,000 kilometers per hour while their bodies absorbed radiation, while their suits kept the vacuum from reaching their skin, while the engineering between them and the most hostile surface in the accessible solar system held its margins. When you look at these photos as a technical document rather than an inspiration poster, what they show is not a destination, it is a threat assessment. The Shackleton crater, because the crater is the reason the Artemis program is targeting the lunar south pole in the first place, and because the photos of it reveal something that the mission briefings discuss in careful technical language that most public reporting does not translate into plain terms. The permanently shadowed regions inside Shackleton and the other craters at the lunar south pole have not seen direct sunlight for potentially billions of years. The temperatures inside these shadows, measured by orbital instruments and confirmed by surface probe data, sit at approximately 40 Kelvin, 40 degrees above absolute zero, cold enough that volatile compounds, including water ice that arrived via comet and asteroid impacts over geological timescales, have been preserved rather than sublimated away. This is why the South Pole matters. The water ice confirmed in these permanently shattered regions is the resource that makes a sustained lunar presence economically and logistically viable. Water for drinking, water electrolyzed into hydrogen and oxygen for propellant, water as radiation shielding mass. The presence of water ice at the lunar South Pole is not speculation. It is confirmed by multiple independent instrument packages on multiple orbital platforms. The photos show the surface above these deposits. They show the terrain the Artemis surface missions will need to navigate to reach them. And they show, if you are looking at them as a field geologist rather than a public affairs officer, exactly how difficult and exactly how dangerous that terrain is. The lunar regolith visible in the high-resolution images is not soil in any sense that the word implies familiarity or safety. The texture visible at 8,000 pixel resolution confirms what the Apollo sample analysis established and what every subsequent remote sensing measurement has reinforced. The surface of the moon is covered in a material that has been produced by 4.5 billion years of impact events occurring in the complete absence of the atmospheric and hydrological processes that round and smooth and chemically alter terrestrial sediment. Every grain in the images is the direct product of fracture, angular, sharp-edged, electrostatically charged by continuous solar wind bombardment, sized in the range that penetrates deepest into the respiratory system when inhaled, and chemically reactive at its surface in ways that make it biologically aggressive to soft tissue in a manner that has been compared in the peer-reviewed literature to asbestos exposure. The photos show this material covering every surface in the frame. They show it coating the rims of small craters. They show it accumulated in the low points of the terrain in deposits whose depth is difficult to determine from orbital imagery, but whose extent is total. The Artemis surface crews will be moving through this material. It will coat their suits. It will work its way into every joint and seal and mechanism through the electrostatic attraction that makes lunar dust one of the primary unresolved engineering challenges of the entire program. The photos document the problem. The solutions are still being validated. The shadows in the images deserve more attention than they typically receive in public discussion of the Artemis imagery. On Earth, shadows are temporary. The sun moves, the angle changes, the shadow shifts, and eventually the terrain it covers receives direct illumination. On the moon, in the regions near the poles that the Artemis program is targeting, some shadows are permanent. The geometry of the moon's axial tilt, which at approximately 1.5 degrees is nearly perpendicular relative to the plane of its orbit, means that the sun never rises more than 1.5 degrees above the horizon at the poles. Craters with walls high enough to block this near-horizon sun create interiors that are in permanent shadow. Permanently, not seasonally, not for geological epochs. Permanently, for as long as the crater has existed in its current form. The interior of Shackleton crater has not seen direct sunlight for perhaps 3 3 billion years. The images show this shadow as a hard geometric edge where the sunlit rim meets the interior darkness. Instruments can measure temperature and volatile content inside these shadows by indirect means. Cameras cannot image inside them with visible light because there is no visible light there. The darkness in these images is not a photographic artifact. It is the real absence of photons in a region that has been lightless for longer than complex life has existed on Earth. When the Artemis crews descend into these regions to access the water ice deposits, they will be working in artificial illumination inside a darkness that predates the evolution of the human visual system by billions of years. The photos show exactly where that darkness begins. The edge is sharp and it does not move. Now consider what the photos do not show. The radiation environment that the crew of Artemis II flew through during the lunar flyby is invisible to any optical instrument. The cosmic ray flux passing through the capsule hull and through the crew members' bodies at a rate that their dosimeters were recording continuously cannot be imaged. The solar energetic particle environment that the current solar maximum is generating at elevated intensity relative to any Apollo mission is not visible in an 8,000 pixel image of the lunar surface. The Van Allen radiation belts that the crew passed through twice, once on the outbound trajectory and once on the return, are not in the frame. The photos show the surface of the moon with extraordinary clarity. They do not show the environment between the surface and the crew. That environment is documented in the mission's radiation exposure records, in the dosimetry data that will be published in the post-mission health assessments, in the blood sample analyses that will measure the biological response to the radiation exposure the crew accumulated over 10 days in deep space. The photos are the visible record. The dosimetry is the invisible record. Both are part of what the mission documented. The press releases discuss the photos. The post-mission medical literature will discuss the dosimetry. The gap between those two conversations is where the real technical audit of what the crew experienced lives. The far side pass is the portion of the mission that the photos from the flyby make most vivid, and that the mission timeline makes most stark in terms of what it required of the crew and the hardware. During the period when the Orion capsule passed behind the moon and the moon's mass blocked all direct radio communication with Earth, the crew was operating in a communication blackout that lasted between 30 and 50 minutes, depending on the specific trajectory. Not a degraded communication link, not a high-latency connection, no connection. The deep space network antennas that had been tracking the capsule continuously since departure were receiving nothing. The mission controllers at Johnson Space Center were monitoring the last known telemetry state of the vehicle and waiting. The crew inside the capsule was executing their observation schedule, operating their cameras and science instruments, managing the capsule systems, and doing it all without the ability to report anomalies, request guidance, or confirm that their planned actions were consistent with what the ground teams would recommend given current system states. The autonomy that the far side pass required of the crew is not a capacity gap that training fills completely. It is a fundamental constraint of the mission geometry that places the crew in a position where they are the entirety of the decision-making capacity available to the mission for the duration of the blackout. The photos taken during the far side pass are the product of that autonomous operation. They are images taken by 4 people who were, at the moment of acquisition, the farthest from help than any human beings who had ever existed. The faces in the mission photos are worth examining as carefully as the lunar surface photos, not to look for signs of undisclosed biological harm, which is not what the images show, but to look for what sustained deep space exposure actually does to human faces in ways that the physiology of the environment predicts and the photos confirm. Fluid redistribution in microgravity produces the characteristic facial puffiness that astronauts experience within hours of entering weightlessness, as the fluid that gravity normally pools in the lower body redistributes toward the upper body and head in the absence of the gravitational gradient. 10 days of this redistribution is visible in comparison photos taken before launch and during the mission. The eyes of crew members who have been in microgravity for extended periods show the effects of the intracranial pressure changes that fluid redistribution produces, a phenomenon that NASA's Human Research Program has been studying intensively because in longer duration missions, the intracranial pressure elevation can produce visual impairment and structural changes in the optic nerve that persist after return to Earth. The skin tone changes visible in long-duration spaceflight photography reflect the cardiovascular adaptations of the body to the microgravity environment. None of this is concealed information. All of it is published in NASA's Human Research Program documentation and in the peer-reviewed literature on spaceflight. The faces in the photos show people who have been in space for 10 days. The physiology of 10 days in space is documented and measurable, and